Okay, in section 7.2, we're going to learn about a new distribution. It's called, let's borrow some space up here. It's called the T distribution. And it has a little bit fatter tails. It's a little skinnier in the hump, and then it looks like this. Okay. Conversely, the normal curve looks like this. The tails are a little bit closer to the x-axis. It comes up and has kind of a more bell-shaped dome, and then it goes down like that. So this would be the normal curve. And this one here would be the T distribution. But we're going to learn in this section that the T distribution depends on sample size. In fact, as the sample size n gets bigger, the T distribution becomes the normal distribution. So as sample size grows, like 100 or 200 or 500 or 1,000, this shape will actually change and it will morph into the normal curve. So why do we use it then? We use it because T distribution is good for any size n. So if you remember, we were very cautious about the normal distribution. We said for the normal distribution, n should be bigger or equal than to 30. And that kind of made us pause on some of these problems that we've worked in this class, because some of the problems, just to make our hand calculations doable in a reasonable time frame, we worked with like size n is 5 or 6 or 10. And we were doing normal stuff with it, but you can't really do that, because the normal distribution really works best when you have sample sizes bigger than 30. So this T distribution would allow us to work with these smaller sample sizes. Okay, so that's all the theory we pretty much need for right now. We'll learn a few new equations today, but otherwise it's very similar. So in the normal curve, we just looked things up on a table. Same thing today. The T distribution, we're going to look things up in a table. It's a different table, but it's in the back of your note packet, so you all have it. Okay, so let's look at 11. Refer to the accompanying data display that results from a sample of airport data speeds in megabits per second. Complete parts A through C. So they give us the confidence interval. They give us the mean speed in megabits per second. They give us the standard deviation of the sample data, and they tell us there were 50 data values. So n is 50. Okay, so even though n is 50, they still want us to use the T distribution, which is fine. It doesn't hurt that we have, that if we have more than 30, we can still use the T distribution. It's good for any sample size. So the first thing it says is, what is the degrees of freedom? So the degrees of freedom will be the easiest calculation you ever do in this class. Degrees of freedom is equal to n minus 1. So I take this n value of 50, and I subtract 1, and I say my degrees of freedom are 49. 49. Then it says find the critical value of T alpha over 2. So if you recall, we had this alpha over 2 idea in the last class. So alpha over 2 is how much error you have in your confidence interval. So if I have and I should probably have drawn that more like a T distribution, but it's fine. So if I have a T distribution, I have 2 flags, one here and one here. And in between these two is my confidence interval. My confidence interval, CI. So in this one, I want to be 95% confident. that's a confidence level of 0.95, which means I have 0.025 that I could be wrong in this tail, and I have 0.025 that I could be wrong in this tail. Notice these three numbers must add up to 1. So here's how this works. If I have a 95% confidence level, my alpha, which is where I can be wrong, is 1 minus the confidence level, is 1 minus 0.95, is 0.05. So this alpha has been split into two regions, 2.5% here, 2.5% here. So we have, this would be T alpha over 2, and this would be minus T alpha over 2. This is pretty much the same drawing we learned last lesson, except instead of, we called it Z's here, now they're T's. That's it. Otherwise, the approach is exactly the same. Now we go to the new table, the T distribution table, and like I said, you have this in your notes. And all we need to know is two things. Alpha over 2, or actually, let's go with alpha, that's easier. All I need to know is alpha, 0.05, and my degrees of freedom of 49. So here's how you use the table. Okay. On the left is degrees of freedom. So all I have to do is go down to 49. So I go down, and there is no 49, but there's a 50. So that's close enough for us. So I'm going to go to the 50 degrees of freedom. But now the harder part is picking which column. So up here, the way this table works is these numbers are your alpha values. And then these numbers, if you notice, are just half of these. So these are your alpha over 2 values. Our alpha in this problem was 5%, so we're right in the middle. Notice the area in one tail would be 0.025, which is what I wrote here. So we need the middle column, and we need to go down to 50 on the left. So we're down to right about here in the middle, where those two intersect. The critical T value is 2.009. 2.009. So this would be 2.009, and this would be minus 2.009. Those two flags would separate my 95% confidence level. So, but I just need one number here. I just need this 2.009. Oh, I just saw that it said rounded 2 decimal places, so we'd call this 2.01. 2.01. Okay. Give a brief general description of the number of degrees of freedom. So since that's a new term, I'm just going to give you the answer and we'll look at it. So the number of degrees of freedom, the answer here is B. The number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. And there's a more complicated understanding of that, but let's just leave it, it's kind of the amount of variation we can have. Just leave it as that in the sample values. Okay, so that's the first problem. Let's look at 12. 12 says, what does it mean to say that the confidence interval methods for the mean are robust against departures from normality? Choose the correct answer. It's actually easier to answer this question with the next problem. So let me give you the answer here, and then we'll see the next problem will really kind of drive the point home. So the answer here is D. The confidence interval methods for the mean are robust against departures from normality, meaning they work well with distributions that aren't normal, provided that departures from normality are not too extreme. And there's a lot of kind of subjective ambiguity there. So let's kind of see a picture and see if that helps us decide how this works. So here is a histogram based on salaries of, I think this one's recent graduates, something like that. Oh, player salaries. Oh, football player salaries. Okay, so football players on a team. And if we plot this, so what did we do with histograms? We use histograms to get the shape to see if they were bell-shaped. So if I were to draw this one, I would start down here at the x-axis, jump way up to this bar, grab it, come down to this bar, then this one, then this one, then this one, go down to 0, and then jump up again here. And I would say, does this shape look like our classic bell shape? And hopefully all of you would shake your head and say, no, it does not. It does not look like that. In fact, this is skewed right, if you recall, which is to say that this right tail is much longer than this left tail. And it looks like there's an outlier out here. So there's a couple issues there. Back when I first introduced normal curves, I said if it's skewed right, we won't even touch it. And outliers have to be dealt with very carefully. But here's the thing. When we're doing confidence intervals of means, we can analyze this. So even though it's skewed right, we're still going to use our confidence interval technique. Okay, so this problem actually doesn't really ask us to do any math. It just asks us which is appropriate, t or z, and then what would be the critical value. So let's outline kind of when I would use which one. First, I use z. If they give me sigma, the population standard deviation, if this is given, then I'm going to use z. If the sample standard deviation is given, I'm going to use t. So notice there's a subtle difference here. This is a population number, so this is the number for the big group of people. This is the sample number. This is the number for the small group of people. I will generally use z only if n is bigger than or equal 30, and I will use t for any size n. And that's about it. So we'll just use these conditions to decide if I use the t distribution or the z distribution. So notice, in this problem, they gave us the standard deviation of all salaries for every football player. So this sigma is given. And our sample size n is bigger than 30. So we have both things checked off here. So let's use the z distribution, the normal distribution with critical z-scores. Okay, then this is easy because to find the critical z-score, we just have to recall that table we built last class. I can reproduce it here fairly simply. We had alpha, confidence level, and then your z alpha over 2. And if you recall, the values we had were 90, let me call it 0.90, 0.95, 0.99. So if I'm 90% confident, I'll have 10% that could be wrong. If I'm 95% confident, I have 5% that could be wrong. Notice these just add up to 1. 99% confident, I'm 1% alpha. The z-scores for this were 1.645, 1.96, and 2.575. So I just have to see what confidence level do I want for this problem. We want 95% confident, so we are right here in the middle. So for 95% confidence, the z-score is 1.96. And just make sure that you select the right bubble. So it's a z-score, and rounded to 2 decimals, it's 196. Okay, let's look at 14. Okay, so it says, a data set includes 110 body temperatures of healthy adult humans. So let's first identify. N is 110. So the sample size is 110. Having a mean of 98.1. So that's X bar. And a standard deviation of 0.64. Now you have to be careful. This 0.64 is for the sample. So this is S. Construct a 99% confidence interval for the mean. So let's write that. Confidence level is 0.99, which means alpha is 0.01. And why not? Let's write what alpha over 2 is. Alpha over 2 would be half of that, 0.005. Now, because S is given, not sigma, we're going to use a t distribution. So in these problems, they actually give you the t distribution you can click on and look at, or they give you the normal z charts that we've been using. So you're not going to look at these z charts because we're picking t. So you'd click on this t distribution table, and it will spit out the following for you to look at. Okay, so here we are again. Now we know, oh, we forgot to do one thing. To use this table, we need to know the degrees of freedom. So that would be what? 109. So degrees of freedom is just one less than the n. So it's 109. So we're looking up 109, an alpha of 0.01, alpha over 2 of 0.005. So these, again, these numbers here are alpha values, and these numbers above them are alpha over 2 values. So we're looking for the 0.01, which is right here, and we're looking for alpha over 2 of 0.005, which is right above it. So this first column is the one we want. So now we just need to go to a degrees of freedom of 109. So we're going down, first column, and just like the previous problem, there is no 109. So the closest one would be 100. 100. So if you look real carefully, it's 2.626. 2.626. So our t alpha over 2, 2.626. Okay. Now the whole point of this is we're trying to form a confidence interval about the mean body temperatures of all humans based on this sample of 110 people. So here's the formula for the, let me write it down here. So we're going to have, you take the mean, subtract your margin of error. That's going to sandwich the mean, which is sandwiched by the mean. And be careful here. This is sample mean, this is population mean. So we're using the sample mean to predict the population mean. And in one case, we subtract margin of error, and in another case, we add margin of error. But that then begs the question, what is the margin of error? Well, in a problem like this, margin of error is equal to your t alpha over 2 value times your sample standard deviation divided by the square root of the sample size. Let's box that, and let's box this, because we're going to use those many times. So our margin of error for this problem is that t value we looked up, 2.626 times s, which was given as 0.64, all divided by the square root of 110, the sample size. And if you're very careful about punching this in your calculator, you should get a margin of error of 0.1602. And they want you to round to 3 decimals, so I'm going to keep 4. Now we're just going to plug this number in here. So they told us the mean was 98.1, so you have 98 0.1 minus this E that we just found, 0.1602. Then you have 98.1 plus that 0.1602. If you subtract this number here, add this number here, you should get 97.9, well, I'll just write it, 9397. And you should get 98.2602. Rounded to 3 decimals, we'll call it 97.940. So just notice the rounding here. This is going to make that a 10, which makes this a 4, which makes that a 0. This one's going to be this 0. No, this 2 makes that nothing, so we drop it. So it's 98.260. Okay, so that's the main part of the problem, is getting that interval. But let's stop and interpret what that means. So we are saying we are 99% confident that all human body temperatures should be, the mean of all human body temperatures should be between 97.94 and 98.26. Then the last part says, well, that's interesting because we're always told you should have 98.6. But how does that compare to this range? So if we were to plot this on a number line, and this is commonly what you want to do, is actually look at this interval on a number line. Over here is our 97.94. Somewhere over here is our 98.26. So this is our interval that we're 99% confident in. Where's 98.6? That's not even in this interval. Notice it's quite a bit bigger than 98.2. It's somewhere over here. So this is strong evidence that the mean body temperature is lower than 98.6 because the entire interval is lower than it, B. And this is exactly how you make strong arguments using statistics. You take a sample, you choose a confidence level, you do the math, and then you see if the value you expect is above the interval, inside the interval, or below the interval. And that can tell you powerful things. Let's try another one just so we can make sure we got this. So if we look at 15, okay, 15. In a test of the effectiveness of garlic for lowering cholesterol, 49 subjects, so N is 49, were treated with garlic in a processed tablet form. Cholesterol levels were measured before and after the treatment. The changes, so your before cholesterol minus your after cholesterol, after the garlic pill, in their levels of LDL cholesterol have a mean of 3.4. So that's X bar. And a standard deviation of 16.6. So that's S. Construct a 95% confidence interval. So our confidence level is 0.95. So we know with a 0.95 confidence level, the alpha is 0.05. Before we get too far, we have to decide, are we using the T table or the normal table? Notice sigma was not given, S was given. So because S was given, let's use the T distribution. So it turns out to be exactly like the problem we just did, except our degrees of freedom are different and our confidence level is different in this one. Since we know we're using the T distribution, let's write down our degrees of freedom. If N is 49, DF is 48. Let's write down alpha over 2 just so we have it. 0.025, just half of 0.05. So now we can go to the T table and find our critical value. So we're looking for, these numbers are for alpha, these numbers are for alpha over 2, left to right. Our alpha is 0.05, so we're right here in the middle. The alpha over 2 is 0.025, that's confirmed right here. So middle column, and we're looking for DF of 48. So we're going down, and just like before, there is no 48, but there's a 50, so this number should look familiar, 2.009. So 50, middle column, 2.009. So that is T alpha over 2. Okay, our margin of error is that T value times the standard deviation divided by square root of n. So for this problem, it's 2.009 times S was 16.6 and N was 49. And if you do this carefully, you should get a margin of error of 4.764. So our confidence interval again will be x bar minus e and x bar plus e. X bar was given to be 3.4. So minus this 4.764. And then 3.4 plus this 4.764. And if you get this right, and then you round to 2 decimal places, you should get minus 1.37 and 8.17. So those are the final answers after you do this and then round. Okay, just like before, let's plot this on the number line. So we have zeros right in the middle. This is minus 1.37 over here somewhere. And then 8 would be over here. And in this region here, we are 90, what was our confidence? 95% confident. Okay, now let's stop and think about what they're doing here. They are measuring people's cholesterol before this treatment and then after this treatment. Ostensibly, what we want is, and I have to be careful here because I can't remember if you want your LDL to be high or low. Does anyone remember? Which one is it that you want to be high? Is it the LDL cholesterol? Yeah, I can't remember. One number you want high, one number you want low. Let's forget LDL and let's just say cholesterol. So let's just say we want it low, right? Just for argument's sake. For it to be low, that means your cholesterol after this treatment should be a smaller number than before. A smaller number subtracted from a bigger number gives a positive result, right? So you would want to be over here in the confidence interval, the positive numbers. Now let's think about what the negative number would mean. That means your cholesterol after the treatment is actually higher than before, which is not something you want. So you don't want this number to grow if it's the bad cholesterol. And so you don't want negative numbers. Now let's think about this. What would a 0 mean? How do I get a 0 out of this equation, before minus after? So this means you're right that your cholesterol before the pill and your cholesterol after the pill is exactly the same, which means this treatment for cholesterol is Useless, right? Now here's the thing. Any of these numbers are equally likely in a confidence interval. So you can't say this negative number is more likely to occur than a 0 than it is an 8. So it is very likely that 0 is the true difference in these numbers. Therefore, your pill is useless. In fact, that's going to be very common in the chapters moving forward. We're going to do this a lot. We're going to say, is 0 in this interval? Because if it is, then we're going to typically say the treatment doesn't work. So the best answer is A. The confidence interval limit contains 0, suggesting that the garlic treatment did not affect the LDL cholesterol levels. Okay, let's try 16. Okay, 16. Listed below are the amounts of net worth in millions of dollars of the 10 wealthiest celebrities in a country. So N is 10. Construct a 90% confidence interval. So CL equals 90%. What does the result tell us about the population of all celebrities? Do the data appear to be from a normally distributed population as required? So because N is less than 30, we're going to use a T distribution. There's actually two reasons for this. One, N is less than 30, but also sigma was not given. So those were our two conditions to use the T distribution. Now this one, they want you to do the T distribution by hand, but we're never going to do that in this course when we have the computer. So we're going to just run these 10 numbers through StatCrunch. Here's how you're going to do it. So somewhere next to these numbers should be like a little window within a window. So you're going to click that, and then let me give you the steps down here for how you'll solve this using StatCrunch. So after you click the window in a window button, you'll say open in StatCrunch. Then you'll click the stat button, and it should drop down options for you. Of those options, you'll select T-stats for the T distribution. Then you'll select one sample, because we only have one sample of one set of numbers. Then you're going to click on the words variable 1, which will load these 10 numbers into the computer. Then you're going to select confidence interval for mu button. So there'll be like a little bubble or a circle or a button, however you want to think about it. You're going to select that bubble. Then you're going to change the confidence level to 0.90 because they wanted us to be 90% confident. I think it defaults to 95% confidence, so you have to change it from 95 to 0.90. And then you'll click compute. And it has to calculate a lot of things. It has to calculate the sample mean, the sample standard deviation. It has to calculate the critical t-score. It has to calculate the margin of error. It has to do all that stuff, but it's going to do it instantaneously. And it's going to spit out a table. And that table, there's only two numbers you need. And it's going to be labeled like this. It's going to have L period limit for lower limit. And it's going to have U period limit for upper limit. So you're going to look for those labels, and you're just going to pull the numbers right off the table. And for this problem, your lower limit is 150.1. This is for my 10 numbers. Now your 10 numbers will probably be different. And then my upper limit for my numbers was 190.9 after I rounded to one decimal. So that's it. That's all there is to it. Just punch it in the computer correctly with those steps I gave you, and then it'll spit out the right numbers. Okay, now we have to interpret. So the next question says, what does the result tell us about the population of all celebrities? So this would be the mean. This would be the mean net worth of what? All celebrities, or, so in these problems we have to be very careful about what is our sample consisting of. This sample was the 10 wealthiest celebrities in a country. Can we use those 10 people in a country to speak about celebrities across the whole world, across all countries? No, that's exactly right. So we can only say that this would be the mean net worth of celebrities in that country specifically. So the wording has to be exactly the same. So we would say here, A, because the 10 wealthiest celebrities are not a representative sample, this doesn't provide any information about the population of all celebrities. Okay, then part B says, does the data appear to be from a normally distributed population? So if you recall, way back in chapter 5 or 6, I can't remember which one, we looked at something called a normal quantile plot. And in StatCrunch, it's called a QQ plot. So you have to go back to your notes and find the steps to do a QQ plot in StatCrunch. It's pretty simple. You're just going to do the same steps here. Open in StatCrunch, but instead of stat, you're going to do graph, and then you're going to do QQ plot, and I think there was 1 or 2 other steps, and then compute. Again, see chapters 5 or 6 for those notes. I've got them outlined nicely in one of those chapters. And in this problem, here's what it will produce. You'll get these dots that are pretty close to a straight line. And if you recall, that's what we wanted. You remember that when we looked at those dots and we said, is that straight enough? That was the whole point of it. These dots are really close to a straight line, but if you look closely, there's that S pattern, that wavy pattern, and we said we don't like patterns. So if you have any kind of pattern other than just straight line, that's going to indicate not normal, not normally distributed. Okay, so in this one, we're going to say, do they appear to come from a population that's normally distributed? No. So these yeses are gone. No, but the points in the normal quantile plot lie reasonably close to a straight line and show some systematic pattern that is a straight line pattern. So no, the pattern is not straight line. So D. Because the points lie reasonably close to a straight line, but there is a systematic pattern that is not a straight line pattern. It's that wavy pattern. Okay, let's look at 17. 17 is actually pretty simple. We have an IQ test is designed so that the mean is 100 and the standard deviation is 10 for the population of normal adults. So notice, standard deviation of a population, we give that the symbol sigma. So sigma is given. If sigma is given, that's going to indicate Z distribution. Find the sample size necessary to estimate the mean IQ score of statistics students such that it can be said with 90% confidence that the sample mean is within 7 IQ points of the true mean. Assume that sigma is equal to 10. We already identified that. And determine the required sample size using technology. Okay, so the equation for this one is the following. Your sample size is equal to your critical z-score times the times the population standard deviation divided by the margin of error that you pick squared. So we saw a formula similar to this back in the last section. So it's just a little different because we know the sample standard the population standard deviation. Now, if you recall that first table, one of the first tables I refreshed our memories on was this one. What's your Z alpha over 2 for confidence levels? So if they want to be, what did they say, 90% confident, that's a Z alpha over 2 of 1.645. So we can replace this Z alpha over 2 with 1.645 times sigma, which is 10 in this problem, divided by E. But what's E? So when they give you a number like this, they want something within 7. So this term here within is saying plus or minus. So this is saying plus or minus 7. So E is 7. So the margin of error is 7. Multiply, divide, get a number, square it, and it will turn out to be 5.5, which we will round up to 6 people. Not a great example because 6 is so small you probably wouldn't want to use a Z distribution, but they've picked a large margin of error. So as the margin of error shrinks down to 2 or 1 or 0.5 or something, this number grows quite a bit actually. So you might get a huge number here. It just depends on what they have for your problem. But now we ask, is it reasonable to sample 6 students? Yes, of course. So the only time you have to think about this is when the N is in the thousands. Then you have to think about, well, can I actually talk to 1,000 people and get their information? But 6 would be easy. Okay, 18, I believe is the last computation one. Okay, the salaries of 47 college graduates who took a stats course in college have a mean X bar of 68,300, assuming a standard deviation sigma of 11,614, construct a 90% confidence interval for estimating the population mean mu. Okay, so N is 47. Sigma is given to be 11,614. So because of these conditions, N bigger than 30, sigma given, we're going to use the Z, keep calling it the Z distribution. I shouldn't call it that. It's the Z score for the normal distribution. But that's fine. We're going to use Z values. 90% confidence. So we just looked that up. The Z alpha over 2 for that was 1.645 from that little table that we've been using. Now our error is going to be that Z alpha over 2 value times sigma divided by the square root of N. So it's very, very similar to the error for the T table. So this is going to be 1.645 times sigma, which is 11,614, divided by the square root of 47, and you should get 2844.35. And that's in dollars. So our interval is the sample mean, subtracting the margin of error, adding the margin of error, and our sample mean for this one is 68,300. So I've got 68,300 minus this 2844.35, and then 68,300 plus that 2844.35. And you want to go all the way to the penny for these, so they don't count it wrong. And if you subtract this number and add this number respectively, you should get 65,456. And I should have had a penny value here. I'm not sure where. Oh, rounded the nearest integer. Okay, that's good. And then we have 71,144. So we're 90% confident that the mean salary of all college graduates is between 65,000 and 71,000. Don't get too excited. They make these numbers up. Okay, last two are theory on how we did these. So which of the following is not a property of the student t-distribution? The student t-distribution has the same general symmetric bell shape, that's true, as the standard normal distribution, but it reflects the greater variability that is expected with small samples. That is stated even better than I said it, and that's all true. The student t-distribution has a mean of t equals 0, that's true. Just like the normal curve starts at 0, so does the t-distribution. The student t-distribution is different for different sample sizes, that's also true. I talked about how it changes shape as your sample size gets bigger. So the last one has to be the one that's not true. The standard deviation of the student t is 1. That does not have to be true. In fact, we did several problems where s was not 1. It was some other number. Okay, last question. Which of the following calculations is not derived from the confidence interval? So if you take your upper confidence limit and your lower confidence limit, add them, divide by 2, that will give you x bar. That's true. If you take your upper confidence limit and subtract your lower confidence limit, that will give you double the margin of error. If you take your upper confidence limit minus your lower, divide by 2, that will tell you what your margin of error was. The only one that doesn't work is A. Adding those two limits does not tell you mu. That's false. And now we'll complete section 7.2.